So we need to write the importance and rule for partitioning of matrix. Well, so large matrices can be partitioned using a system of horizontal and vertical lines. Clearly, a given matrix can be divided into blocks in different ways. So, for example, if we have a matrix A, which is 4 by 5 matrix, so it's pretty big. For instance, the entries are 1, 2, 3, 7, 0, 5, 2, 9, 0, 2, 4, 4, 7, 0, 1, 4, 4, 6, 7, 11, 2. So this is 4 by 5 matrix. And when we partition this matrix, we basically divide it into blocks. For instance, we could do it this way, but there are a lot of different ways to do it. So if we divide it this way, we get 6 different matrices, and we could write down that matrix A equals matrix E, F, matrix G, H, I, J. So basically these sub-matrices, these blocks, become entries of matrix A. And they're basically the arrays indicated by dashed lines. Also, this matrix A can be partitioned in different ways. So for instance, we can write it as, we can divide it into blocks as one second. So we can divide it into blocks as here, here, and here. So again, we have 6 blocks, but obviously these blocks are different. These are different arrays. And again, our matrix A consists of E, F, G, H, I, J arrays. So this shows that a matrix can be partitioned in many ways, but the new blocks can be of different size and different order. So the matrix entries of such a partition matrix are called submatrices or blocks. So this is submatrices or blocks. So now we need to discuss the importance for partitioning of matrix. Why do we need to do this and how it helps us? So it's useful when it's applied with the very big matrices, because the operations can be carried out more easily on the smaller blocks of this matrix. And on operating the partition matrices, the basic rule can be applied to the blocks as though they were single elements. So we can you can work with these blocks as with matrices if you want to do any operations, but you also can work with all of them together as with just with elements of matrix A. So this gives you a lot of freedom. And for instance, if M is a square block matrix such that the non-diagonal blocks are all 0 matrices, then it's called a block diagonal matrix. The importance of block diagonal matrix is that the algebra of the block matrix is frequently used on the algebra of the individual blocks. So we can write down that M is diagonal block, where it's A11, A22, ANN. So it's frequently used reduced to the algebra of the individual blocks. So suppose f of x is a polynomial and M is the above mentioned block diagonal matrix, then f of M is a block diagonal matrix, and it's diagonal of f of A11, then f of A22, and so on to f of ANN. Also, this matrix M is invertible if and only if each AII is invertible, and in such case the inverse of M is a block diagonal matrix too. So the inverse of M equals the diagonal block matrix of A11 inversed, A22 inversed, and so on until ANN inversed, and all these components need to be invertible. Also, a square block matrix is called a block upper triangular matrix if the blocks below the diagonal are zero matrices, and a block lower triangular matrix is the blocks above the diagonal are